The determination of the absolute configuration of chiral molecules is an important aspect of molecular stereochemistry. The main traditional methods of establishing absolute configuration include X-ray crystallography, synthesis of the molecule under study through a series of stereochemically controlled steps, optical rotation and electronic circular dichroism. Among these methods, only X-ray crystallography is an absolute method. Although straightforward and highly reliable, this method requires a single crystal of the sample of sufficient size and quality, a requirement which is not easily met and often may be even precluded. In order to determine the absolute configuration of the crystal unambiguously, an atom heavier than oxygen must be present in the molecule or must be incorporated into the molecule by derivatization. Here again, the derivatization step should not alter the chirality under investigation. The stereochemically controlled synthesis is prone to error if an unexpected reversal in stereochemistry occurs at any step, and in addition is time and effort consuming. For relating the sign of the measured optical activity to absolute configuration, several rules or useful correlations have been established for a variety of structural motifs. However, such empirical methods should be carefully addressed since might be contaminated by incorrect assignments. CD has been used as a relative method based on chirality rules. Unfortunately, all these rules involve exceptions and in fact places some doubt on the use of empirical rules. Vibrational circular dichroism became lately an increasingly popular method for the unambiguous assignment of the absolute configuration in chiral molecules. VCD is the extension of electronic circular dichroism into the infrared region where fundamental vibrational transitions occur. VCD has number of advantages over all the previous methods of absolute configuration assignment, but has some limitations as well. Like X-ray crystallography, VCD is an absolute, not a relative method, but unlike X-ray analysis, does not require the presence of an heavy atom in the molecule and is not restricted to single crystals. VCD spectra are recorded for neat liquid or solution in suitable solvents like CdCl3, CCl4 and carbon disulfide, and no derivatization of the molecule is needed prior to analysis. The VCD method of analysis involves comparison of the experimentally measured VCD spectrum to the one calculated from ab initio quantum chemistry. If close agreement between the measured and calculated IR and VCD spectra is achieved, the absolute configuration is established by comparing the signs of the experimental VCD to the signs of the spectrum calculated for a particular choice of absolute configuration. Should these signs be same, the absolute configuration is the calculated one. If the signs are reversed, the absolute configuration is the opposite of the calculated configuration. After studying this module, you shall be able to know about assignment of absolute configuration of chiral coordination complexes using optical rotatory dispersion, learn about assignment of absolute configuration of chiral coordination complexes using circular dichroism. Learn about assignment of ligand conformation using circular dichroism. Identify the absolute configuration or chirality of a chiral coordination complex. Identify the ring conformation of the ligand for chiral coordination complexes. Optical rotatory dispersion is the variation in the optical rotation of a substance with a change in the wavelength of light. Optical rotatory dispersion can be used to find the absolute configuration of metal complexes. For example, when plane polarized light from an overhead projector is passed through a cylinder of sucrose solution, a spiral rainbow is observed perpendicular to the cylinder. Principles of rotation. When white light passes through a polarizer, the extent of rotation of light depends on its wavelength. Short wavelengths are rotated more than longer wavelengths per unit of distance because the wavelength of light determines its color. The variation of color with distance through the tube is observed. This dependence of specific rotation on wavelength is called optical rotatory dispersion. In all materials, the rotation varies with wavelength. The variation is caused by two quite different phenomena. The first accounts in most cases for the majority of variation in rotation should not strictly be termed rotatory dispersion. It depends on the fact that optical activity is actually circular birefringence. In other words, a substance which is optically active transmits right circularly polarized light with a different velocity from left circularly polarized light. In addition to this pseudo dispersion, which depends on the material thickness, there is a true rotatory dispersion which depends on the variation with wavelength of the indices of refraction for the right and the left polarized light, for right and left circularly polarized light. For wavelengths that are absorbed by the optically active sample, the two circularly polarized components will be absorbed to differing extents. This unequal absorption is known as circular dichroism. Circular dichroism causes incident linearly polarized light to become elliptically polarized. The two phenomena are closely related, just as are ordinary absorption and dispersion. If the entire optical rotatory dispersion spectrum is known, the circular dichroism spectrum can be calculated and vice versa. Optical rotatory dispersion and circular dichroism are very useful in determining the absolute configuration of any complex. CD and ORD spectra can be used to identify between two enantiomers of the chiral complex. Compounds with the similar structures give similar ORD or CD spectra if they have the same absolute configuration. The essence of the method is to recognize that molecules of identical configuration should have the same Cotton effect for electronic transitions of the same origin, whereas enantiomers will have mirror image Cotton effects. Now, the difficulty is to determine the absolute configuration of one and more coordination complexes which can be used as standard. This was solved by Bijouet, who used the method of anomalous diffraction of X-ray to determine the absolute configuration of sodium, rubidium, D-tartrate. The method was then applied to a cobalt complex, and it was found that the complex had this configuration and the enantiomer of the same complex had opposite configuration. Therefore, it is now possible for this complex to be used in determining the absolute configuration of the other cobalt complexes using ORD and CD. Assignment of absolute configuration using optical rotatory dispersion. Optical rotatory dispersion involves measuring the variation of optical rotation with wavelength. There is abrupt reversal of rotation in the vicinity of absorption band. If the complex is levorotatory, the ORD curves falls to a minimum, rises rapidly to a maximum, and then slowly falls. If the complex is dextrorotatory, the effect is reversed, for the ORD curve rising first to a maximum, then falling, etc. These represent positive and negative cotton effects. ORD curves are useful in the assignment of absolute configurations. For example, the configurations of the enantiomer of tris-ethylene diamine cobalt 3, tris-alanylato cobalt 3 and bis-ethylene diamine glutamato cobalt 3 are known from X-ray diffraction technique. It is found that the 3 lambda plus enantiomers or lambda d enantiomers of these complexes have similar ORD spectra. On the basis of lambda configuration can be assigned to any of these complexes in the absence of X-ray data, simply on the basis of the similarity of the ORD spectra to one of the known configuration. For ORD spectrum to be instantly recognizable, no other absorption must be nearby. The ORD spectra lambda tris-ethylene diamine cobalt 3 plus, lambda S-alanylato cobalt complex and S-glutamate cobalt 3 complex are shown here. All three complexes represent positive cotton effect spectra, where En refers to ethylene diamine, S-alanine refers to the anion of S-L-alanine, and S-glu refers to the dianion of S-L-glutamic acid. All of these complexes have the lambda or D configuration. Although ORD was used extensively at one time because of simpler instrumentation, circular dichroism is currently much more useful. Assignment of absolute configuration using circular dichroism. The circular dichroism refers to differential absorption of left and right circularly polarized light. That means epsilon L minus epsilon R. Complexes having same sign of CD for a given absorption band will have the same absolute configuration. The absolute configuration of tris-ethylene diamine cobalt 3 complex had to be determined first for the assignment of absolute configuration of the other related complexes. The absorption and CD spectrum of the complex is shown here. The CD spectrum of cobalt complex suggests that the lambda isomer shows positive deflections. However, the delta isomer shows negative deflections in CD spectrum, which also corresponds to the sign of the cotton effect. The CD spectrum of the complex shows the presence of another absorption band at approximately 24 into 10 raised to power minus 3 centimeter inverse. That is not obvious from the absorption spectrum. Tris amino acido cobalt complexes were prepared using amino acids. CD spectra of these complexes illustrate the application of circular dichroism for the determination of configuration. If 3 glycinate ligands are bound to a metal ion, 2 diastereomers, FAC and MER are possible, and each of these will have an enantiomer. However, if a substituted amino acid such as alanine, R-alanine or S-alanine is used, complex can still exist as 2 geometrical isomers, both of which are chiral. It explains FAC and MER. The arrangement of ligands about the metal ion can result in lambda or delta chirality. However, the right-handed FAC isomer is not enantiomeric with the left-handed FAC isomer. For example, the use of S-alanine can give the FAC lambda isomer shown here. A mirror image of this complex cannot be generated with S-alanine because the enantiomer necessarily contains R-alanine. Therefore, FAC delta isomer is a diastereomer of FAC lambda. This is the same case with MER isomers. The net result is that while FAC and MER isomers have an enantiomeric partners, if the glycine is used, however, the optically active amino acid will give a diastereomer for each chirality of each FAC or MER isomer. All the 4 isomers shown here and 6 are diastereomers, easily separable from one another under achiral conditions. Each one of them is having different physical properties. The FAC and MER isomers show distinct stereoscopic properties from one another. The FAC isomers give rise to similar UV visible spectra. Similarly, the MER isomers also give rise to similar UV visible spectra. The absolute configuration of the optically pure alanine complexes can be assigned by comparing their CD spectra to those for optically pure tris-ethylene diamine cobalt 3 complex. The absorption and CD spectra for the 4 diastereomers of S-alaninate cobalt 3 is shown here. The sign of the cotton effect for the lowest energy CD band of the FAC plus and MER plus isomers is positive, just as it is for lambda plus tris-ethylene diamine cobalt 3 complex. This result strongly suggests that these complexes have the same absolute configuration lambda. The sign of the cotton effect for the lowest energy CD band of the FAC minus and MER minus isomers is negative, suggests that they have an absolute configuration opposite to that for the plus isomers. This result suggests that these complexes have the same absolute configuration delta. It should be noted that the CD curves for the plus and minus isomers are not exactly mirror images of one another. This is due to the fact while the complexes have opposite absolute configurations based on the positioning of chelate rings, they are in fact diastereomers as mentioned above. This arises because only S-alaninate was used as ligand. Assignment of ligand conformation using circular dichroism. As we are aware that in trischelate octahedral complexes, dissymmetry can also be generated by using disymmetric ligand. For example, the Gauch conformation of ethylene diamine is disymmetric and could be resolved were it not for the almost complete absence of the energy barrier preventing racemization. Attachment of the chelate ligand to a metal retains the chirality of the Gauch form, but the two enantiomers can still interconvert through a planar conformation at a very low energy, similar to the interconversions of organic ring systems. Thus, although it is possible to describe two enantiomers of the complex such as tetraamine, ethylene diamine, cobalt 3+, but it is impossible to isolate them due to rapid interconversion of the ring conformers. In this case, two enantiomers of a complex are possible due to delta or lambda chirality of the ethylene diamine metal ring. If two or more rings are present in one complex, they can interact with each other and certain conformations might be expected to be stabilized as a result of possible reductions in interatomic repulsions. For example, consider a square planar complex containing two chelate rings of ethylene diamine. There can be three structures possible: M delta delta, M lambda lambda, M lambda delta. The first two isomers lack a plane of symmetry, but the last one is a mesoform. Corey and Baller showed that the M delta delta and M lambda lambda are the most stable as compared to the last one. This is due to the fact that the meso compound has unfavorable HH interactions of axial-axial and equatorial-equatorial type between the two rings. Similarly, for an octahedral trischelate complex, we might expect to find 4 forms. All these forms are optically active, so there can be 8 isomers in total, but only 2 isomers are isolated. This stereoselectivity is most easily followed by using a chiral ligand such as propylene diamine. The configuration of the plus enantiomer of the ligand has been shown to be S if the molecule in this configuration is attached to a metal. 2 conformations are possible. The conformation with the methyl group in an equatorial position is most likely as compared to the one with the methyl group in axial position. Note that the S propylene diamine theta conformation is the mirror image of R propylene diamine lambda conformation. Therefore, If the diamine or R configuration is used, the conformation of greater stability should be lambda. If R is combined with cobalt 3 sulfate and oxygen, two isomers of empirical formula are isolated and they are not enantiomeric to each other. Instead of having equal and opposite rotations as expected for enantiomer, they have specific rotation of -24 degree and +214 degree. However, S ligand also gives two diastereomers, but these have rotation of +24 degree and -214 degree. It is clear that R ligand and S ligand have given two pairs of enantiomers, one pair having R or S ligands with specific rotation ±24 degree and another pair again with R or S ligands with specific rotation ±214 degree. An X-ray analysis of the minus complex indicates that all the three chelate methyl groups are cis to one another. Second, the absolute configuration is delta. The chelate rings are in expected delta conformation. Therefore, assuming that methyl groups are cis to one another in all the complexes, the enantiomeric pair must have delta conformation with the rings arranged in lambda conformation. The authenticity of this analysis can be confirmed by CD spectra of plus complex, which is similar to delta plus trisethylene cobalt complex. In contrast, the CD spectrum of minus complex is opposite to the same complex. Configurational assignment in natural products. The survey of recent literature reveals an increase in the number of papers dealing with configurational assignment in natural products by VCD technique. This fact may be easily explained from the experimental point of view. There are not restriction for the physical state of the compound. A small amount of sample is required and compounds only enriched in one enantiomer, not enantiomerically pure, are still acceptable. However, the ab initio calculations might be much more difficult since the molecules are generally large, involve several chiral motifs and may adopt unexpected conformations. An usual strategy used in these cases is fragmentations of molecules, selecting a core structure relevant for the chirality of the whole molecule and calculation of the fundamental vibrational mode in the selected moiety. Summary. In this module, we discussed that assignment of absolute configuration of chiral coordination complexes using optical rotatory dispersion and circular dichroism. CD and ORD spectra can be used to identify between the two enantiomers of a chiral complex. Compounds with similar structures give similar ORD or CD spectra if they have the same absolute configuration. The essence of the method is to recognize the molecules of identical configuration should have the same cotton effect for electronic transition of the same origin, whereas enantiomer will have mirror image cotton effects. If two or more rings of ligands are present in one complex, they can interact with each other and certain conformations might be expected to be stabilized as a result of possible reductions in interatomic repulsion.